thunderstorm is a weather factory which produces thunder, lightning, rain, snow, hail, and varying degrees of turbulence. The purpose of this film is to explain the formation and structure of the thunderstorm. There are two general types: air mass thunderstorms and frontal thunderstorms. Air mass thunderstorms may result when the sun heats a surface, causing warm, moist air to rise and cool. Over land areas, these storms generally occur during the afternoon and early evening. When air moves out over a warmer body of water, the lower layer of air is warmed and rises convectively, producing the same type of storm. These storms may occur at night or during the day, but usually reach their most intense development at night when the land-water temperature contrast is the greatest. Air mass thunderstorms also occur when moist, conditionally unstable air is pushed up a mountain slope. They may be isolated over peaks or quite general along the range. Cold front thunderstorms occur when a wedge of cold air moves into a region of unstable, warmer air, supplying the required lifting action. These storms generally are concentrated along a front which is often hundreds of miles long. The line appears to be continuous, but between these closely knit storms are clouds of comparatively mild turbulence. Warm front thunderstorms occur when warm, conditionally unstable air flows up the slope of a retreating wedge of colder air. Warm front thunderstorms are difficult to locate because they are masked by other clouds. Generally, they are widely scattered and not as common as cold front thunderstorms. Thunderstorms vary greatly in size. Those from 12 to 15,000 feet high are usually not as severe as the largest storms, which range up to as much as 60,000 feet. Smaller storms, however, may be severe at certain stages in their development. Storms generally vary from 5 to 25 miles in diameter. Some extend 50 miles. Also, thunderstorms vary in size with the season. In summer, they reach maximum height. In winter, thunderstorms are infrequent. Three factors are required to form a thunderstorm: air of high moisture content, some type of lifting action, and conditionally unstable air. To explain what conditionally unstable air is, let's assume this is altitude, and this is temperature in degrees centigrade. We know that air which is not saturated, when lifted, cools at the dry cooling rate of 3 degrees per 1,000 feet of altitude, as shown by this line. We also know that saturated air, when lifted, cools at the wet cooling rate of approximately 1.5 degrees per 1,000 feet of altitude, as shown by this line. Temperature at various altitudes can be plotted for a given column of air. For purpose of illustration, let's use a column in which temperature decreases uniformly with altitude. When this temperature decreases at a rate between the dry and wet cooling rates, the air is conditionally unstable. This temperature plot represents the temperature distribution with respect to altitude at a given time. To explain how this instability is released, let's consider this parcel of air in a column of unsaturated air about to be lifted. The parcel is represented by this dot on the temperature plot. Initially, the parcel has the same temperature as the surrounding air, in this case, 20 degrees. When the parcel is lifted, it expands and cools at the dry cooling rate of 3 degrees per 1,000 feet. As it cools, it gets closer and closer to saturation. Eventually, it becomes saturated. The slightest additional lifting will expand and cool the parcel further and produce condensation of liquid water on condensation nuclei, which are usually present in abundance in natural air. As the moisture in the parcel of air condenses, the heat of condensation is released, which slows down the rate of cooling of the parcel being lifted from 3 degrees to approximately 1.5 degrees per 1,000 feet. Until this time, the parcel has been colder than the air through which it has been lifted. Now, due to the slower cooling rate, it approaches the temperature of the surrounding air. If lifting is continued, the parcel will become warmer than the surrounding air. It is then relatively lighter, and it will be accelerated upward by the weight of the surrounding air. Thus, it will continue to rise until it is cooled by radiation and mixing to the temperature of the air around it. The release of conditional instability, therefore, promotes intense cloud growth. And so these 3 factors, high moisture content, lifting action, and conditionally unstable air, working together, may produce a thunderstorm. No matter how thunderstorms are formed, and regardless of their size and intensity, the basic characteristics are the same. Within the thunderstorm are one or more regions of vertical drafts called cells. These cells may be as much as 5 miles in diameter, and draft velocities may vary from a few feet to as much as 100 feet per second. In the early stage of development, the cumulus stage, an updraft prevails throughout the entire cell. As it develops further into the mature stage, there is both an updraft and a downdraft. And finally, in the anvil or dissipating stage, there is a downdraft in the lower 2/3 of the cell, with little or no vertical motion in the upper third. In and around each draft, the airflow is turbulent. Small eddies or whirling bits of air are driven by and superimposed upon these drafts. Some of these gusts are very small, and some are hundreds of feet in diameter. The frequency of occurrence and intensity of the turbulence encountered is usually greatest between 10 and 20,000 feet. The region of greatest turbulence is associated with the height of the freezing level. Between cells, with their drafts and gusts, are areas of relatively little turbulence. Let's trace the development of a single thunderstorm cell. In the cumulus stage, the updraft is fed by gently converging surface winds. Air is drawn in through the sides of the cell. The cell grows in height. As the warmer, moist air rises through the colder environment, condensation occurs. The droplets formed concentrate into larger drops. In time, the weight of these drops becomes too heavy to be borne by the updraft. They begin to fall. As rain reaches the earth, the cumulus stage ends and the mature stage begins. The falling drops of water or ice particles drag on the rising air current and create a downdraft of colder air. This air, being colder than the surrounding air, accelerates in its downward movement. This develops both downward and horizontally at the expense of the updraft. These up and down drafts create gusts whose maximum intensity is at or slightly above the freezing level. Minimum turbulence is encountered in the vicinity of 6,000 feet. The downdraft reaches the earth as a cold core of air in the rain area, spreading out along the surface. It extends as much as 5 miles in front of the advancing storm cloud, reducing surface temperature and producing strong, gusty surface winds. In the mature stage, rain is found in the lower levels, mixed rain and snow in the middle levels, and snow and ice crystals in the upper levels. During this stage, hail may be encountered occasionally, especially above 10,000 feet. It sometimes falls out of an overhanging cloud into clear air. The downdraft spreads throughout the cell until it cuts off the updraft. This ends the mature stage and begins the dissipating or anvil stage. The updraft vanishes. So does the source of rainfall and energy. Gradually, the rain ceases. The downdraft weakens and turbulence diminishes gradually. This stage of the cell usually is indicated by the anvil shape. However, the appearance of an anvil in a cloud is no indication that it is a dissipating one, since there may be several cells in various stages of development. Every thunderstorm cell passes through these three stages: cumulus, mature, and dissipating, producing turbulence, thunder, lightning, rain, hail, snow, and ice crystals. The intensity of any storm is dependent on its stage of development. A multicellular storm contains cells which are in various stages of development. Each successive cell tends to attain a greater height because one feeds the next. A new cell absorbs saturated air from earlier cells rather than the relatively dry air which surrounds an isolated cell, thus developing some of them into new thunderstorm cells. While an isolated thunderstorm cell may last about an hour, a cell which is part of a multicellular storm may endure more than twice as long. The process gradually stops as the three basic conditions causing thunderstorm activity disappear. Since the turbulence in a thunderstorm is centered in the vertical draft areas, it is important to determine which regions are storm cells and which are merely masking clouds. Occasionally, this may be done visually. The sun shining through this line of thunderstorms outlines the dark areas, indicating the turbulent storm cells. The storm cells may be revealed by flashes of lightning. The dark area under a cloud, indicating the area of heaviest rain, also shows the location of the thunderstorm cell. Crash static on the radio indicates that there are thunderstorm cells nearby. Radar is being used more and more in the study of thunderstorms, both on the ground and in the air. The storm echoes on the PPI scope indicate the bearing and distance of the thunderstorm area. The direction of movement of a storm cell may be indicated by the characteristic anvil top and shelf of clouds which may extend many miles in front of the storm. This is the direction in which new storm cells may be expected to develop. This line of thunderstorms, as seen from 18,000 feet, is about 130 miles distant. The anvil tops reach 35,000 feet. The shelf clouds hide the bases from a high-flying plane. They also hide the tops from a low-flying plane. And so, briefly, thunderstorms are divided into two general types: air mass thunderstorms and frontal thunderstorms. A thunderstorm is made up of one or more cells, regions of vertical drafts and gusts which produce turbulence. This turbulence is greatest at or above the freezing level, which is normally found in the upper two-thirds of the storm. Each cell passes through a life cycle of three stages: cumulus, mature, and dissipating. The anvil tops and shelf clouds indicate the general direction of thunderstorm movement. In this day of all-weather operation, a basic understanding of the characteristics of the thunderstorm is essential.